Hello, this is the Mathematic Fanatic, and you are watching Wolfram Alpha Can't Solve This Crazy Integral. So, first a little introduction. To start off the video with a preface, I only have the basic version of Wolfram Alpha, not the pro version. So it may be able to find the solution with more time allowed, but I doubt it since when I was trying to do the same integral in a different form, it found a complex numerical answer, rather than the analytical answer I found in the real numbers. The integral we are solving today is the limit as t approaches infinity of the integral of negative t to t of e to the negative x squared all over 1 plus x to the 4 sine x all dx. So I created this integral based on a video from Flammable Maths, which I will add in the description. One key note though, that even though this method was invented by him, or at least I believe it was and so does he made a mistake in explaining it in his video, which I will correct here. And it's not my correction, the comment section already corrected it, but I'm going to use it here. So first things first, let's get to the Gaussian integral. That is very similar to the one we have. So the Gaussian integral we can solve using polar coordinates. The Gaussian integral is the integral from negative infinity to infinity of e to the negative x squared dx. So the way to compute this with polar coordinates is pretty cool. However, the indefinite version of this integral is non-elementary, meaning there is no antiderivative. I will not prove that in this video because it really doesn't matter to the solution. It's irrelevant. So if we take I equals the integral that we're looking for, the Gaussian integral, then I squared equals that integral squared, which then, by change of variables for one of them, you can do the integral here in terms of x times the integral here in terms of y. And that's because changing the variable is a trivial substitution of x equals y. So dx equals dy. Therefore, we are able to combine the two integrals into a double integral, since neither integral depends on each other. So that's where we get the two integrals from different variables equals the double integral from negative infinity to infinity of each, e to the negative x squared times e to the negative y squared. So that ends up being this thing right here, the double integral from negative infinity to infinity for each of e to the negative, in parentheses, x squared plus y squared, all dx dy. Then converting this into polar coordinates, we can do the substitution x equals r cosine theta and y equals r sine theta, which gives us dy dx equals r dr d theta. Now, this is because we have to multiply by the Jacobian determinant, which turns out to be r. I will compute that for you now. So dx dr, dx d theta, dy dr, and dy d theta, which, if you just take that, it's cosine theta, negative r sine theta, and r cosine theta. Taking the determinant of that, you get this because it's a times d minus b times c. So you end up getting r times all cosine squared plus sine squared of theta. So you end up getting equals r because cosine squared plus sine squared equals 1 for any same theta. So, however, personally, I never really understood why we multiply by the Jacobian determinant until I just had a realization while watching Mathemaniac's video on the Jacobian, which I will link in the description. I wasn't really sure if this is proper. This is just a realization. I don't know if it makes perfect sense, because he didn't necessarily say it explicitly, but it came to my mind that the Jacobian determinant is the higher dimensional version of the derivative that we would multiply during u sub. Rather than just multiplying by the derivative of a single variable, you multiply by the higher dimensional version, which kind of makes sense to me. I don't know if it's perfectly logical though. So back to the integral at hand. We can find what x squared plus y squared is in terms of r and theta. Well, so we have r cosine theta squared plus r sine theta squared equals r squared times cosine squared theta plus sine squared theta, which just equals r squared. And the bounds no longer go from negative infinity to infinity. The bounds for r go from 0 to infinity, since the radius can't be negative. And the bounds for theta go from 0 to 2 pi, since you are rotating around the entire circle of the plane. So we end up getting this integral that we had before equals the integral from 0 to 2 pi of the integral from 0 to infinity of e to the negative r squared r dr d theta. Then using u sub for u equals r squared, we get du equals 2 r dr. So that gives us what we have before equals the same integral bounds of e to the negative u over 2 du d theta, which then we can integrate e to the negative u over 2 from 0 to infinity, which ends up giving us just 1/2 in that part. So it'd be the integral from 0 to 2 pi of 1/2 d theta, which equals just theta over 2 from 0 to 2 pi, which equals pi. And since that was actually I squared, we take the square root of both sides to get I equals the square root of theta. So a general form rule that we are going to use, that the one that I chose seems completely random for this specific general rule, but it just seems hard, so that's why I did it. But this is the general form that Flammable Maths came up with. The general form is the integral from negative a to a of e of x over 1 plus t of x to the o of x, where a is a constant, e of x and t of x are any even function, and o of x is any odd function. An even function is a function that satisfies the property f of negative x equals f of x for all x, and an odd function is a function that satisfies the property f of negative x equals negative f of x for all x. And that integral, what we have before, is the same as the integral from 0 to a of e of x dx. And I will prove that for you using the corrected proof, because I believe in his video he did not say that one of them has to be even. He said only one has to be even, not two. So e of x and t of x both have to be even. So there's a way to separate any function into its odd and even parts, which is actually pretty cool, and I believe is how hyperbolic sine and cosine are derived, or at least that's what I feel like I've come to realize. I was never really told much about those functions in my academic career, though. So the method is to take any function f of x, and then the even component is e of x, I should say capital E of x, equals f of x plus f of negative x over 2. And the odd component is O of x equals f of x minus f of negative x over 2. And that's capital O of x as well. So this is because clearly, without even using algebra, you can see that e of x plus O of x equals f of x. And I'll show you why. So you have f of x over 2 and f of x over 2. Those add together just to give f of x. And f of negative x over 2 minus f of negative x over 2, those cancel out to be 0. So it equals f of x when you add them together. Just by plugging them in, you get e of x and O of x are even and odd respectively, just because plugging in negative x for them, you get the same thing. Then the integral of an even function with symmetric bounds is twice the integral from 0 to one of those bounds. And the integral of an odd function with symmetric bounds is 0. These are common properties of symmetric integrals that you can look up if you're interested. There are bound to be plenty of resources on that. So we get for f of x, we get e of x over 1 plus t of x to the o of x. Then what I meant to do is negative a to a of f of x equals the integral from negative a to a of e of x plus o of x, where those are capitals, which equals just 2 times the integral from 0 to a of the capital E of x dx, because the o of x cancels out and the e of x is doubled, and the bounds are halved. So we end up getting, plugging back in capital E of x for what we have, we get this. But then the 2's cancel out, 2 and 1/2 cancel out, to give us just the integral from 0 to a of f of x plus f of negative x all dx. Which then we can plug into the definition of f of x. Then we can plug this back in for f of x and f of negative x to get exactly what f of x, f of negative x are. So we can then simplify, because e of negative x, because e is even, is just e of x. T of negative x, because t is even, is just t of x. And o of negative x, because o is odd, is just negative o of x. So then each function is even or odd respectively, which is why we can do that. So then we can get a common denominator by multiplying each side by 1, which is the other denominator over itself. To get, this is our original, this is what we get. Now you have a common denominator. And so since when you multiply them together, it equals the added of them together. And really the only term you have to check is the 1 on the last term, because anything to a power times itself to the same negative power is 1, since the negative exponents cancel out with each other, making adding the denominators the same as multiplying them. Since there's a common term of e of x in each of the fractions, you can add the other parts on top, and canceling out everything for e of x just gives us our second proposed identity. So now, we know the identity and the value of the Gaussian integral. We can add those together to find the limit as t approaches infinity of the integral from negative t to t of e to the negative x squared over 1 plus x to the 4 sine x dx. First, to show that e to the negative x squared is even. So e to the negative x squared is the same as e to the negative x all squared, because negative x squared is just x squared, which was simple. But now we have x and 4 sine x. But x is odd, not even. However, we can break x to the 4 sine x into x to the 4 all to the sine x. And x to the 4 is an even function, since it is an even degree polynomial. And finally, sine of x is an odd function, which is well known. So we get this integral is the same as of just the limit as t approaches infinity of the integral from 0 to t of e to the negative x squared. However, we know that e to the negative x squared is even. This is now 1/2 times the symmetric bounds, which we know that the symmetric bounds as t approaches infinity ends up being just square root of pi. So we end up getting 1/2 times square root of pi, which is the square root of pi over 2. And finally, we are done. Thank you.